Oversized service conductors may be specified for several reasons. Firstly, future expansion might be a factor. The drawings may anticipate future loads or equipment upgrades that require higher capacity. Secondly, voltage drop considerations can lead to oversizing. Oversizing conductors can reduce voltage drop over longer distances, ensuring adequate voltage supply to the fire pump. Thirdly, code requirements might dictate larger sizes. Some codes may require larger conductor sizes based on load calculations or maximum distances. Finally, safety margin is a consideration. Engineers may err on the side of caution and specify larger conductors to provide ample capacity for the fire pump's operation. To determine the appropriate service conductor size for a fire pump controller, follow these steps. 1. Calculate the load. Determine the maximum demand of the fire pump, including the pump starting amps and running amps. 2. Apply a diversity factor. This factor accounts for the fact that all pumps do not operate simultaneously. A typical diversity factor for fire pumps is 70%. 3. Multiply the load by the diversity factor. This gives you the adjusted load. 4. Refer to NEC Table 310.16. This table provides conductor ampacities based on the type of conductor and ambient temperature. 5. Select a conductor size. Choose a conductor size that has an ampacity equal to or greater than the adjusted load. 6. Adjust for voltage drop. If the distance from the service to the controller is significant, you may need to calculate and adjust the conductor size to compensate for voltage drop. Regarding lug size discrepancies, if the controller breaker lugs are smaller than the specified conductor size, you may need to adjust the termination method. Consult with the manufacturer of the controller to determine if special terminals or adapters are available to accommodate larger conductors. Let's delve further into each of these points, providing a more comprehensive understanding of the factors influencing conductor sizing and the methods used to calculate appropriate sizes. When considering future expansion, it's essential to look beyond the immediate needs of the fire pump. Think about potential upgrades to the fire suppression system, which might involve larger pumps or additional equipment. Designing for future capacity upfront can save significant costs and disruptions later on. This involves assessing the long-term plans for the facility and anticipating any increased demands on the electrical system. For example, if there are plans to expand the building or add more sprinkler heads, the fire pump may need to be upgraded to handle the increased water demand. In such cases, it's prudent to specify larger conductors initially to avoid the need for costly rewiring in the future. Voltage drop is a critical consideration, especially in installations where the fire pump is located a significant distance from the main electrical service. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause the fire pump to operate inefficiently, reduce its performance, and potentially damage the motor. The amount of voltage drop depends on several factors, including the length of the conductors, the current flowing through them, and the conductor's resistance. To minimize voltage drop, larger conductors with lower resistance are used. The National Electrical Code provides guidelines for allowable voltage drop in branch circuits and feeders. For fire pumps, it's crucial to maintain voltage drop within acceptable limits to ensure reliable operation. The NEC recommends limiting voltage drop to 3% in branch circuits and 5% in feeders. Calculating voltage drop involves using Ohm's law and considering the conductor's impedance, which is affected by its material, size, and temperature. Various online calculators and software tools can assist in performing these calculations accurately. Code requirements play a significant role in determining conductor sizes for fire pumps. The National Electrical Code provides specific rules and regulations for the installation of fire pumps, including conductor sizing, overcurrent protection, and disconnecting means. These requirements are designed to ensure the safety and reliability of the fire pump system. NEC Article 695 specifically addresses fire pumps and outlines the requirements for their electrical installations. It covers topics such as the separation of fire pump circuits from other electrical systems, the use of approved equipment, and the coordination of overcurrent protective devices. The code also specifies minimum conductor sizes based on the fire pump's rated horsepower and voltage. It's essential to consult the latest edition of the NEC and any local amendments to ensure compliance with all applicable requirements. Safety margin is another important consideration when specifying conductor sizes for fire pumps. Engineers often incorporate a safety factor to account for uncertainties in load calculations, variations in ambient temperature, and potential future increases in demand. A safety factor provides extra capacity to ensure that the conductors can handle the fire pump's load under all operating conditions. This is particularly important for fire pumps, as they are critical life safety equipment that must operate reliably in emergency situations. The size of the safety factor depends on the engineer's judgment and the specific characteristics of the installation. However, it's generally recommended to provide a safety factor of at least 25% above the calculated load. This means that the conductor should be sized to carry at least 125% of the fire pump's full load current. When calculating the load of the fire pump, it's essential to consider both the running amps and the starting amps. The running amps, also known as the full load current, is the current that the pump draws when it's operating at its rated capacity. The starting amps, also known as the inrush current, is the current that the pump draws when it's first started. The starting amps can be significantly higher than the running amps, typically ranging from 300% to 600% of the full load current. This high inrush current can cause voltage dips and potentially trip over current protective devices. To accommodate the starting amps, the conductors must be sized to handle the peak current without excessive voltage drop. The NEC provides guidelines for sizing conductors for motor starting applications, which should be followed when sizing conductors for fire pumps. Applying a diversity factor is another important step in determining the appropriate conductor size for a fire pump system. The diversity factor accounts for the fact that not all pumps in a multi-pump system will operate simultaneously. In many fire protection systems, there are multiple fire pumps connected to the same electrical service. However, it's unlikely that all of these pumps will be running at the same time. The diversity factor represents the ratio of the maximum demand of the system to the sum of the individual loads. A typical diversity factor for fire pumps is 70%, which means that the maximum demand of the system is assumed to be 70% of the sum of the individual pump loads. This factor can be used to reduce the conductor size, as it's not necessary to size the conductors to carry the full load of all the pumps simultaneously. Referring to NEC Table 310.16 is essential for determining the ampacity of conductors. This table provides the allowable ampacities of various types of conductors based on their size, insulation type, and ambient temperature. The ampacity of a conductor is the maximum current that it can carry continuously without exceeding its temperature rating. NEC Table 310.16 lists ampacities for conductors and free air conductors installed in raceways or cables. The ampacity of a conductor is affected by the ambient temperature, as high temperatures reduce the conductor's ability to dissipate heat. The table includes correction factors for ambient temperatures above 30 degrees Celsius, which must be applied to the ampacity values. When selecting a conductor size, it's crucial to choose a conductor with an ampacity that is equal to or greater than the adjusted load, which is the load calculated after applying the diversity factor. Adjusting for voltage drop is a critical step, especially when the distance from the service to the controller is significant. As mentioned earlier, voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the impedance of the conductors. The amount of voltage drop depends on the length of the conductors, the current flowing through them, and the conductor's resistance. To compensate for voltage drop, the conductor size may need to be increased. The NEC provides formulas and guidelines for calculating voltage drop. These calculations involve considering the conductor's resistance, the length of the run, and the load current. Various online calculators and software tools can assist in performing these calculations accurately. If the calculated voltage drop exceeds the allowable limits, the conductor size must be increased until the voltage drop is within acceptable levels. Regarding lug size discrepancies, It's not uncommon to encounter situations where the controller breaker lugs are smaller than the specified conductor size. This can occur due to various reasons, such as manufacturing tolerances, design limitations, or the use of different standards. In such cases, it's essential to consult with the manufacturer of the controller to determine if special terminals or adapters are available to accommodate larger conductors. Some manufacturers offer lug adapters that can be used to connect larger conductors to smaller lugs. These adapters are designed to maintain a secure and reliable connection while complying with all applicable safety standards. Alternatively, it may be necessary to use a different termination method, such as reducing the conductor size at the termination point. This involves using a reducing connector to connect the larger conductor to a smaller conductor that fits the lug size. However, it's important to ensure that the smaller conductor has sufficient ampacity to carry the load. In some cases, it may be necessary to replace the breaker with one that has larger lugs. This is typically the most expensive option, but it may be necessary if no other solutions are available. Regardless of the method used, it's crucial to ensure that the termination is properly installed and torqued to the manufacturer's specifications. Improperly installed terminations can lead to overheating, arcing, and potentially fire hazards. In summary, determining the appropriate service conductor size for a fire pump controller involves a careful consideration of various factors, including future expansion, voltage drop, code requirements, safety margin, load calculations, diversity factors, and conductor ampacities. By following the steps outlined above and consulting with qualified electrical engineers and manufacturers, it's possible to ensure that the fire pump system is properly sized and installed for reliable operation. Remember to always prioritize safety and compliance with all applicable codes and standards. The information provided in this narration is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer before making any decisions regarding the design or installation of electrical systems. Additionally, stay up to date with the latest edition of the National Electrical Code and any local amendments to ensure compliance with all applicable requirements.